Maybe we wait a minute and then start.
Okay. So let's start.
No, not it is even 7 p.m. right now.
Okay.
When did you stop the recording?
Yes, sir.
Start again and then we will start.
Okay.
Okay, Krishnendu, you can start.
Okay. Okay. So welcome everyone to this evening session of the year-long program at Bhaskaracharya Pratishthan.
When did you stop the recording?
Yes. Yeah. So it's a great pleasure to welcome Professor Fernando Rodriguez Villegas from the International Center for Theoretical Physics. So Professor Villegas is a very reputed and well-known name in this area. So he was a, he has hold a long career and very, at a reputed places. Like he was the member at the Institute for Advanced Study, and he was a faculty member at the Princeton University, University of Texas, Austin, before joining ICTP. He also was the head of the mathematics section at ICTP. So I used to visit when he was head of the mathematics section, and I had many memorable conversations with him. So currently he is a senior research scientist there. So it's a great pleasure, Professor Villegas, to have you here. So now I give it to you for starting the lecture. Thank you very much for coming today.
No, thank you for the invitation, and thank you, Krishnendu, for a nice introduction. So what I will talk about is work I have worked with several people, but the most long-term and most stable collaborator is David Roberts, with whom we just wrote a short note that should have appeared in the June volume of the notices of the American Math Society. I haven't checked, but that's what the plan was. So these two talks are going to be based more or less on that paper. So you can always refer to that, or also ask me later. I'll be happy to try to answer. So let me start really at the very beginning. So integrals such as this, that I think we all have seen in one form or another over the years. It's surprisingly the start of a lot of very interesting mathematics that still continues on more than 200 years later. Integrals like this appear when you try to describe the movement of the ideal pendulum. And usually what you do in a physics class is start with this and then quickly find a approximation, because the integral itself is not something you can express in terms of other more elementary functions. And in the paper we say, I couldn't know for sure, but I'm sure, I feel like it must have been pretty frustrating for people that got to this point and then wanted to continue and couldn't quite express this in other things that they knew. Also, if you try to compute the length of the arc of an ellipse, you end up with integrals of this kind, and hence these integrals are known as elliptic integrals. So this this integral has a series expansion, which is also something very likely that you have encountered before. As this expansion, and this is for t in absolute value less than 1. So this is an example of a hypergeometric series, which are going to be the main actors in these talks, or in the background all the time. So what do we know about this? So the first important thing is that this function satisfies a linear differential equation. By the way, I noticed that Fritz Berkes is going to speak about hypergeometric series functions or series in one variable soon after. So those things will also appear in his talks, I'm pretty sure. So I won't dwell on this too much, but just to set up the scene for what is my interest that is more arithmetic in nature. So it satisfies a linear differential equation of order 2 with polynomial coefficients. And more geometrically, it is a period, and I mean this in a fairly loose sense, as the integral of some differential form on a family of elliptic curves, the Legendre family of elliptic curves, which I'll denote as ET y squared equals x 1 minus x 1 minus tx. So one way to summarize this is to say that f of t is motivic, which I won't try to define too precisely, but basically, if you like, it's a shorthand to say that it comes from integrating differential forms on a family of algebraic varieties, in this case, these algebraic curves, these elliptic curves. So let me just give a sense of where this is going. What I'd like to do is talk about how this fits into a general picture where we're going to be able to associate, at least maybe not so direct connection between something that will be the analog of this hypergeometric series in a more general form with a family of algebraic varieties. And my interest will be more on more than even geometric, on the arithmetic side. So another manifestation of the fact that that we're talking about something motivic is that precisely we can do some arithmetic. And concretely, let me say this now, and I'll come back to it and say a bit more later, that if we consider the same equation, which a priori we were working, didn't quite say it, but we were working over the complex numbers. the equation on its own makes perfect sense, well, basically on any ring. So if we take T to be some parameter in a finite field FQ, we for avoiding certain, let me just, rather than Q, let me just say P. So we can talk about this equation modulo P a prime. It will have a certain number of points. I mean, well, you can do the geometry that you can do on a finite field is to a large extent counting. And it's convenient to write the number of points in this way. And in a technical sense, I'm including the point at infinity. So I'm talking about the projective version of this curve. And these numbers AP of T are a very important quantity. And so I'll come back to this AP of T as a function of T a little bit later. But yet another thing that we can do is pick T to be some rational number. And 0 and 1 are special because the family degenerates and the curves are not really elliptic anymore. So I'll stay away from those. So I take T to be some rational number. Now I have an elliptic curve defined over the rational numbers, and I can do this counting with a fixed T and varying P. So P outside from a finite set that depends on T gives a number AP. Maybe I'll put the T to emphasize that it depends on it, with which we form I mean, there's work here to make complete sense of what I'm going to write, but I'll just say that these are the main ingredients. There's more work to do to get the full force of this series, but this is the L series, which has played an enormously important role in the modern number theory. Just to mention two main important ways in which it plays a role is in the Birchall-Dyer conjecture, and of course in the modularity proved by Wiles and collaborators. So the fact that this example that we're considering, starting with this integral and the corresponding family of varieties, the fact that it's motivic has this other arithmetic life and has all these other interesting objects associated to it. So this is just to set up the scene. In a way, what I like to do is take this picture and see it as an instance of a much larger picture, and try to go and describe in each one of these items that I mentioned for this example, how they appear in the general setting. So this hypergeometric modes are a general form of this framework. Okay, so this is where we're heading towards, and I will set up the machinery to do so, sort of one step at a time. And I'll start by discussing So I'll think of this as the initial seed, the initial data that will lead to all this wonderful arithmetic stuff as the differential equation. But I will take a point of view less from the analysis point of view, more of a more geometric point of view, perhaps. So what that means is that we are going to sort of switch over from the differential equation to something else called the monodrome representation. So let me slowly explain what that means. And this is a bit strange because I have my camera off and I only see my own screen, and so I have no idea what's going on back where you are listening. So please do stop me and ask me questions if there's something that is not clear.
What does the word motivic exactly mean? What is the origin of this word?
Well, the origin of the word, as I understand it, is a letter that Grothendieck wrote to IISER in 1964, where he uses the word motivic or motive in a way that eventually leads into this direction. It's a very complicated thing to be very precise of what that means, although there are several ways of doing it. And I don't think it will, I'm certainly not going to be capable of doing that myself. So I can say just a little bit, at least, of what is the reason for this. I think my reading of the discussion, the early discussion of Grothendieck and IISER, it would seem to me that the main object that he thought of as being sort of a motive was the Jacobian of a curve. So but so if you want to have something sort of to hold on to as what could this be referring to, I think it wouldn't be wrong to think that a motive is a piece of a cohomology of an algebraic variety that's been cut out in a sort of natural way. For example, it can be cut out by automorphisms. So it could be that you have a variety which has a group of automorphisms that act in the cohomology, and you look at the fixed part by the group, or has been cut out by some other geometric means. So I'm purposely, I'm being vague about it, but I would be also, it gets very technical to make this precise. And I think it would be, for my purposes, enough. What another thing what I can focus on is that whatever these motives are, they have L functions. And so the goal could be, for example, just be able to produce things like the L function of an elliptic curve in a more general setting. I don't know if that helps.
Okay, so last time you were saying that they have L function, meaning all motive or your hypergeometric motives?
No, all motives will have L functions, but the hypergeometric ones are ones that are, as I said in the abstract of the talk, they are very concrete, and they're some of the complications of a general motive have been cut out to the smallest possible way, that where they still are interesting but not trivial. So no, L functions are something that has to do with motives, not just with the hypergeometric ones. Hypergeometric ones are the ones I will talk about because are the ones I can describe in actually fairly concrete ways. Okay.
Okay, thanks.
Yeah. Okay, so to get there, so just to go back, I want to start with something like this series, for example, and I want to see that it's related to a family of varieties in general, algebraic varieties, and I want to ultimately produce an L function. That would be a quick summary of what I like to do. An L function that I don't just want to write down, but I actually will be able to. I want to be able to compute with. So I should say, by the way, that a number of these things I'm talking about have already been implemented in Magma by Mark Watkins. So maybe I can show tomorrow some examples. Okay, so what is this monodromy? So very quickly, if we have an L is a linear differential operator, of some order, n, say. This is all over the complex numbers. And we take, we look at local solutions at some regular point. So some point that is not a singularity of the equation. This so around point, they form a this is a theorem of course.
Your voice is breaking.
Yeah, I don't know.
Now it is okay, perhaps.
Yeah, no.
There is some problem.
For my phone connection, and is it okay now?
Yeah, it seems okay at the moment.
Okay, so this is a space of the dimension n. Start with a solution in V, some local solution. We can analytically continue following some path, a path that avoids the singularities. And when you follow the path, and if you start at your base point and you come back, you're going to get another local solution, which may not be the same one you started with, but will depend linearly on the homotopy class of the path. So what this leads to is to a representation of the fundamental group of P1 minus those singularities into linear transformations of the vector space V. So this is a representation, so it's a homomorphism. If you continue through one path and then you follow by another path, is the same as if you continued on the product of the paths in the sense of the fundamental group. And this monodromy representation, of course, the representation itself depends on various choices you made, but its isomorphism class doesn't. So it's a well-defined representation up to isomorphism. And this is the main object I want to concentrate on now. And it's a sort of a more, I don't know, algebraic or geometric incarnation of the original differential equation. And in a certain sense, it carries all the information you want about it. If you take one of these singularities of the equation and you take a small loop around it that, say, is being oriented consistently, then this will map to some linear transformation let's call it HS of the vector space of solutions. And these things get the name of local monodromies. Okay, so there's a very special situation that occurs. Which is that, so these local monodromies are well defined up to conjugacy, because everything here depends on choices that amount to, if you like, changing bases in your vector space. So you only will typically know these local monodromies up to conjugation. So you could ask, and the special situation is one in which the local monodromies up to conjugation determine rho. So this situation is called rigid, and it's a fairly special situation, but it was a bit of a historical accident that this is always the case for order 2, and which is the case that Riemann, who was the first to think in these terms, faced. So he was proponent of thinking of the solutions, global solutions of the differential equation in terms of the local behavior, which amounts to understanding these local monodromies. So what happens in general is that I will describe what I mean by this, but hypergeometric differential equations are rigid. And this is kind of a miraculous situation, because what it will mean is that very little data that will amount to describing the local monodromies, or the conjugacy class of the local monodromies to be precise, completely determine this representation rho. So by knowing what happens around these singularities, you completely know how solutions of the differential equation will analytically continue along any path. And so what this will allow us is that we will be able to give the equivalent of this differential equation that we started with. I didn't write it down, but I mentioned it, by just simply giving what amounts to very, very little data. And this is how and why we can describe these hypergeometric modes so concretely. Okay. Of course, this requires a proof, but I'm just stating it as a fact about hypergeometric equations, which makes them, in a certain sense, so ubiquitous that they appear in all kinds of situations and subjects. Now, one other fact that we need to know is that if we are after what I mentioned before, is in a sense has no arithmetic, no geometry so far, not much. But if we want to see these equations having come from integrating some form of differential form, some kind of differential form on a family of varieties, we need to know a bit more. The corresponding representation rho is not just arbitrary, it has very special features. And so the key fact I want to mention now is that if a representation rho arises from a geometric family of algebraic varieties, then its the eigenvalues of the local monodromies are roots of unity. Okay, so it's convenient to write the eigenvalues in an exponential form. And so if this is the eigenvalue, we write it as e to the 2 pi I alpha for some alpha, which is certainly only defined modulo integers. But another way to formulate this key fact is to say that alpha has to be a rational number, which is only going to be defined modulo integers, but nevertheless. Okay, so let me then, with this preliminaries, describe what are the hypergeometric. Well, I won't describe too much the differential equation, but what are the hypergeometric, well, let's just call it data, which will lead on one hand to a differential equation and on another to a monodrome representation. So the data will be, so let me just say, maybe I should say something about the equation that the example, I'll use this as a running example. So what can we say about the monodrome representation of this example? So the first thing, so example will be the Legendre family. I'm using it as a running example. First of all, that the singularities are at 0, 1, and infinity, which is in a way the smallest number, which still is interesting. If you only have 2 singularities, is not very interesting at all. So 3 is the minimum, and in a certain sense, hypergeometric differential equations are very tight in the sense that they're as I was saying, the simplest in a sense without being completely trivial. So there's only 3 singularities, therefore there's only 3 local monodromies. And so we have our representation from P1 of C minus 0, 1, and infinity, and some base point I'm not specifying, but different from 0, 1, and infinity. And it will be a representation to a vector space, automorphism to a vector space of dimension n. So it will correspond to order n. In our example, n is 2 for the elliptic curves. And what are the features that it has? We can pick a basis in such a way that the local monodromies have the following features. The local monodrome at a point S being 0 or infinity, is the companion matrix of a polynomial Q sub S, which I'm defining as follows. Q infinity is the polynomial where certain exponents alpha 1 through alpha n. Sorry, I'm doing both the example and the general case somewhat at the same time. I'll explain. And then Q0 is T minus 2 pi I beta 1. So I'm exhibiting the what will be the eigenvalues. So my data consists of a string of n rational numbers alpha and n rational numbers beta. And a companion matrix is one which will have a characteristic polynomial, the polynomial you give it. And concretely, if an eigenvalue appears repeated, it will have a Jordan block with as big size as the multiplicity of that eigenvalue. But you can write it down. You can write down explicitly what that companion matrix is. And so my input data is this string alpha and beta, this 2n tuple of rational numbers. What I'm claiming is that there is a representation rho, which will correspond ultimately to a differential equation in the manner that we were describing. And this representation has 3 singular points, and the local monodromies at 0 and infinity are these companion matrices. This is a result of Levelt in the 60s. And this, I'm missing out the point 1. The point 1, it has its own local monodromy, but since we are in P1 with 3 points missing, the product of these 3 little loops around 0, 1, and infinity multiply out to be the identity in the fundamental group. So we must have this product of the 3 of them being identity. So if I know 2 of them, I know the third. And another feature that that happens with this representation is that H1 is a special type of matrix that it fixes a codimension 1 subspace. So sometimes called a pseudo-reflection. Okay, so I'm claiming that if you give me the alpha and the betas in this form, I can produce a representation rho by assigning to loops at 0 and infinity the companion matrices of the 2 polynomials, defining H1 by this product, and that will give me a representation that will be associated to a differential equation. Now, to continue, I will make this assumption. So if none of the alpha i's equals to one of the beta j's modulo integers, or if you look at the polynomials, if q infinity and sort of q0 with inverting t, sort of read backwards, are co-prime, then this representation is irreducible and rigid, which means that if you give me 3 other matrices that are conjugate individually to these 3 that I wrote down, then the whole triples, all of the 2 triples will be sort of conjugated by 1 matrix simultaneously, all 3. So the corresponding representations will be isomorphic. I'm not sure that's clear enough. I'm doing this backwards from the historical point of view because I'm giving you the representation before I give you the differential equation, which is exactly backwards historically. Maybe I should say something to connect with more of a hypergeometric, historical, or more something that you're more familiar with.
This condition doesn't hold then alpha is not equal to beta j?
Sorry, not. Yeah. So for no alpha I and beta j coincide mod z. Yes, thank you. So the other thing to point out with this form of this statement is that the matrices, these companion matrices, I didn't write down what they are, but I'm hoping you've seen it. This is, as I said, very completely explicit in terms of the coefficients of the polynomial, is that the entries of these matrices are in the same ring as the coefficients of the polynomial. So this is an important fact to point out. A row as image in GLN of a ring R, R being the ring generated by the coefficients of Q infinity and Q0, as well, since you're going to invert matrices, you also will need to invert their determinant, which is equal to this. And so this is a fairly small ring in comparison. It's certainly, you don't have to go all the way to the complex numbers. And in particular, if Q infinity and Q0 have integer coefficients, then R is just Z, because Q infinity 0 and Q infinity 1 will have to be plus or minus 1. And this is the situation we'll be in. This is now getting closer to something arithmetic. So how are we going to use this? I'm going to select the alphas and the betas, which is the same as selecting Q infinity and Q0. And I will choose them to have integer coefficients. Let's see, Armand, you're asking me something. I assume that these results do not apply to more singular points. Do you mean these singular points of the equation?
Than 3.
More than 3.
No, more than, if you have more than 3 points, there are rigid systems, but you have to manufacture them quite explicitly. So what is beautiful about hypergeometrics, among many other things, is that they're easy to describe and they're valid for any dimension, any n, any order. If you give me 5 points, then I can write down some systems which will be rigid, but you would have to sort of work them out individually. There will be the hypergeometric one. There's also another one called Pohammer, but they are not things that are easy to write down that exist in every dimension are basically only those two.
Thank you.
Yep. Yeah, the whole subject of rigid things is fascinating, and that's certainly not the main topic of these lectures. Yeah, no, but I think it's a very interesting thing to think about. So to go back, I more or less described for you that given this data, we have a representation, which I'm going to assume is in this setting, so it's irreducible and is rigid. So just by giving these 2 polynomials, if you like, I, for free, miraculously acquire this representation row. But to connect it to more classical things and things that maybe you have seen, let me assume, to simplify, that, say, the last beta n is equal to 1. Then there is a classical hypergeometric series to connect to the title, which we can write down explicitly in terms of these Pohammer symbols and in terms of these parameters alphas and betas that we chose. And the point of this series is that it is a solution to the differential equation associated to rho. So I went backwards. I gave you first row And then now I'm telling you there is a differential equation, and I'm giving you a solution to that differential equation. And historically, of course, things went exactly the other way. So back to the example, finally. For the Legendre family, what is it that we have? So we have three singularities, t equals 0. And I'm going to write down the Jordan form of the local monodromy. Let me use the exponents. So the eigenvalues are e to the 2 pi I, these numbers that I'm writing down. So the two eigenvalues are 1. So these are the exponents, which are, as we were saying, only defined modulo integers. At 1, we have also a unipotent matrix, and at t equals infinity, we have eigenvalues -1. So the exponents are 1/2 and 1/2. So this is the beta, and this is the alpha. So the example of the Legendre family has alpha equals 1/2, 1/2, and beta equals 0, 0. So we can say that we have encoded, let's go back to the beginning. We have encoded the family of elliptic curves to some extent, the differential equation, and this integral all kind of arose from these two strings of rational numbers. And that's the beauty of this rigidity, that will allow us to choose different alphas and betas and go back and sort of uncover this whole world that they are associated with via this hypergeometric story. And that's, again, pretty much what I like to, the purpose of these talks. So we can give the alphas or the betas, or we can give the polynomials, and it's in some ways nicer to give the polynomials. They would be these two in this case. I think for a benefit of time, I'm not going to write it down, but let me just say that this series, which is a particular solution to the differential equation that we have, has an integral representation due to Euler, which, like in the case of the running example, shows that it is motivic if the alphas and the betas are rational. Yeah, so I always found this really striking, that in analysis and in classical theory of special functions, you will see that giving a certain function you're interested in as an integral of something is an incredibly important thing that allows you to understand your function much better, to give bounds and all kinds of things. And from our point of view, you can boil down this motivic story to its essence by saying, well, this function is motivic because it's given by an integral of something that only involves essential algebraic things. Okay, so we're going to focus on the more arithmetic. Forgot the numbers, maybe 3. We'll focus on the following cases. We're going to focus when the ring R is Z, and which this amounts to saying is that we're going to pick pairs of polynomials Q infinity and Q0 with integer coefficients of the same degree n and coprime, no common roots, and only roots of unity as roots. This is the same, it's a reformatting of the data of giving alphas and betas in Q, none of n alphas and n betas, none of which are equal modulo integers. It's the same repackaging of the same information. And by all of the previous discussion, this whole fairly small amount of data gives rise to a representation row, and which will be associated to, on one hand, a linear differential equation, and on the other, to a family of algebraic varieties, as we will see. Okay, there is yet another repackaging.
If the image of the representation,
Excuse me?
if the image of the representation a discrete subgroup, does it imply any conditions?
Yeah, I know that there's been a lot of interest in this kind of questions. It's not a given that it is. Let me see. In general, but here we.
Do your conditions imply that the image of the representation is discrete?
Not necessarily, I don't think.
I see.
I mean, it's a subgroup of GLNZ, yeah, but that's as much I think we can know at this point.
Of GLNZ, then it's discrete.
Yeah. In general, I think you don't know. Yeah. I mean, if the ring is arbitrary, then yeah.
Yeah. Okay. Okay. So right. So in GLNZ, yeah, that's the strongest. That's the interesting information.
Yeah, absolutely. And I was kept thinking that there is a very important paper of Fritz Böckers and Heckman, who they characterize when these hypergeometric series are algebraic, and the way they do that is by arguing that finite follows from being discrete and compact. And so once we get to this point in this setting, we would like to, if we wanted to find when the group is actually finite, we would like to understand the signature of a Hermitian form that it fixes. So that's also another direction, but these, in fact, will be interesting motives, and I think I will mention some of that example of this on Thursday. Okay, so another another format for the same information. All I'm doing is repackaging the same data in ways that is more convenient for different purposes. So one way to express the same information that I have up there is to say that we look at the ratio of these two polynomials, and let me write it this way, and you'll see it's a bit cumbersome, but you'll see why this is sort of a convenient. So I write it as a rational function with terms like this, which I can because the roots of Q infinity and Q0 are only roots of unity. And this is for certain integers gamma 1 up to gamma L. And so I can just simply give this string of integers, which the order doesn't matter. So I will assume that they're given in non-decreasing order. And the properties that is satisfied is that the sum is 0 because the function, the rational function, is a quotient of two polynomials of same degree n. And moreover, I don't want to have any cancellation, so I don't want any gamma I to be 0, or gamma I to be a negative over gamma j. So I call this thing a gamma vector. So none of this has any depth, but it's just a convenient way to rewrite the same information. So for a running example, gamma is simply -2, -2, 1, 1, 1, 1. Okay, so this is our initial data. What we can say now is that associated to a gamma vector as with the properties listed here, I will, by this miracle of rigidity, associate to that a representation that, as we were saying, maps into GLN of Z. And what it has this hypergeometric series as one of its solutions around t equals 0. It has an integral representation and so on. And I didn't write it down, but the integral representation leads to a way to express this hypergeometric series as an integral of something that you could see as coming from an algebraic variety. But that algebraic variety, this Euler representation, is pretty nasty. So I will associate to this a different family of varieties that is much more amenable to a study. Okay, and I think so. I never checked, but I presume the talk is supposed to be an hour. Is that correct?
Yeah, yeah.
Okay. So I will just write this down, and I will finish there. Okay, so this this whole hypergeometric thing went from classical to another, by now, classical thing, which is the work of Gelfand, Kapranov, and Selevinsky. And they, I think, were the first to describe the following family associated to this data. So let me quickly tell you what it is, and maybe I'll discuss this again starting on Thursday. So I'm going to write down a hypersurface of the torus. D will be L minus 2, L being the length of the gamma. So notice that that the Legendre example, which is sort of the simplest thing to start with, as I did, in fact, has a gamma vector of length 6. And the variety that I will write down in general has dimension L minus 3. So take the simplest example and run this machinery that I'm about to describe. And you, instead of a family of elliptic curves or curves, you end up with a family of threefolds. Well, we'll just live with that. So what will happen is that the dimension of the varieties that I'm going to write down could be much bigger than what you expect them to be. And this is, let me just make sort of a somewhat philosophical comment, that these motives have a bit of a knack to sort of sit themselves in different places. And so the dimension of the variety that can host them, in fact, is not really well defined. And so this elliptic curve sits, the motive that we associated to it sits very nicely by this process of called taste twist inside the a family of threefolds. And it could be also naturally appearing in something of an even higher dimension. So I think of this as a bit of what happens with genes in biology, that they kind of can show up in the DNA of all kinds of different animals. All right, so what do we do? This is purely combinatorial. So I'm going to define this as a zero locus of a polynomial. Let me tell you how we write this. So it's a sum of monomials in d variables in terms of a parameter that I'm calling u. And these monomials are sort of orthogonal to the vector gamma. And this k that I have there, so I will assume for simplicity that these gammas have no common factor. So I can find a linear combination of them that gives me 1. So if I start with my data in terms of this gamma, I look for monomials such that the gamma is an affine relation among them. And so the way I like to think of this is that we're in dimension d, and we have so we have d plus 2 points in d space. So if we had d plus 1 points, then we typically going to just have affinely independent points. But if we have d plus 2 points, then they'll generically will have only one relation, affine relation among them. And this is what I want. I start with, so I think of gamma as a relation, affine relation among d plus 2 points. And I take those d plus 2 points as sort of tight as possible. So what we want is that these monomials span affinely z to the d. Okay, so for example, I mean, there's a maybe I'll stop with this. An example of elliptic curves, but different from the one that of the Legendre family. Let's take gamma to be -3, 1, 1, 1. So sum is 0. No pair adds up to 0. And I could take k to be 0, 1, 0, 0. Then I can take the monomials to be the columns of this matrix 0, 0, 1, 0, 0, 1, -1, -1. Or if I draw them in the plane, so D here, L is here 4, D is 2. So this corresponds to, gives me a family of curves. If I draw the points in the plane, I get this picture, and the convex hull is going to be an important object is going to be the Newton polytope of the equation. So here the family then is 1 plus ux plus y plus x inverse y inverse sitting inside C star cross C star. Okay, so this is just a simple example. And in this case, what we'll see is that we do have a motive of rank 2, which will match the cohomology of this family of elliptic curves. But in general, as I was saying, this procedure, this completely algorithmic procedure, starting with gamma and associating this particular hypersurface of the torus, gives me something of a much higher dimension that, so to speak, naturally this object is associated with. And so one of the issues, depending on what you want to do, in fact, reducing the dimension of this thing that you get algorithmically could be quite complicated. So for example, as I will describe tomorrow, Thursday, if you want to consider the cases of Berkes and Heckman, where the hypergeometric series is algebraic or the monodromic group is finite, naturally, the motives should be simply a field extension, so something of dimension 0. But if you write down this variety of JKZ, you're going to get something that could be much bigger dimension. And so you would, if you want to, what I call chase this motive and understand what it is, you will have to, for example, morally think of an algebraic extension of Q of the parameter as being involved in a family of varieties, say, as we discussed, dimension 7. Depending again on what you want to do, that could be pretty painful. All right, so I'm getting ahead of myself, so maybe this is a good time to stop, and I'll ask questions if I manage. Thank you.
You can open your video.
Okay.
I can open my video.
Thank you.
Let's hope the thing. I'll stop sharing maybe.
Okay.
There we go.
Thank you, Professor Villegas, for this wonderful lecture. Is there any questions?
Thank you. That's a very nice talk.
Thank you so much.
What was in that Sayers letter?
It was a letter from Gotthard to Sayre.
Yeah.
I read it at the time. Unfortunately, I don't think there is a lot that I certainly couldn't make a lot of sense. I mean, he's forming his idea, so it's not a final product. He's kind of trying to explain what he's thinking. So it's naturally somewhat vague.
So that was the only place where he talked about motives? Or?
No, not the only. No. I think that was kind of the first place, if I have my history right.
There are even Tata Institute lecture notes where he talks about them. So,
yeah, no, of course, the whole thing kind of evolved in a big way, but I think that's the first mention.
Okay. So, are there more questions?
So that linear differential operator of order 2 with many singularities can be rigid, right?
For order 2, I think you don't have a lot of room. I think for 2, you only have, basically, I think you only have the hypergeometric one that is rigid.
I see. So
no, wait a minute. What I'm saying, that what happens is there's not a lot of, I mean, if you have 3 points, it's rigid in rank 2, because it is hypergeometric up to some simple scalings.
Okay.
There is famous.
So, yeah, so Professor Kulkarni, yeah, you are asking something, please.
There is the famous papers of Hurwitz on hypergeometric something. So, is that a starting point? So to speak, I mean, these triangle groups also came from that.
I think I only know the paper of Hurwitz where he talks about some order 4 differential equation having to do with modular forms. Maybe, and ultimately it has to do with a Klein group. Yeah, I don't know much more than that, no.
Very good talk. We look forward to your next talks.
Okay, thank you so much. Thank you so much.
Hi, I enjoyed your talk. Unfortunately, I was called away by something I had to answer. So I missed what GKZ stands for.
GKZ stands for Gelfand, Kapranov, and Selevinsky. That they wrote a series.
I know.
Of papers.
It's okay.
Yeah.
So you were referring to that book.
Yes, and they kind of write down this family of varieties. I have to say that if I can see that this family of varieties is related to sort of the hypergeometric stuff by counting points over finer fields, to do it at the level of the complex numbers, I think it's at least never been written down very clearly. It's not easy to say, here's this integral over this family of varieties that gives me this solution to the differential equation.
Is that theoretically possible?
I think it should be, but if you want something explicit, I think I actually don't know how to do it in general. You know, if you look at the literature in physics, in the mirror symmetry and so on for the last, whatever, 20 years, there's many examples, but they tend to be examples where you have a polytope which has an interior point, and then there is not so hard to write this integral. But if you have say a polytope with no interior point, I actually wouldn't know how to do it.
Mm-hmm. So could you say a little bit more about what happens when you have more singular points? Let's say that it's not rigid, then you should have families, right?
Well, so one way to think of this is that you have say a number of points that you fix, say in P1, and then you choose the nature of your local monodromies, or rather the conjugacy class of them. Let's say that's your data, and then you're trying to find all representations that have these local monodromies after conjugation. So that space is a manifold, right, and you can suddenly compute its dimension. And this is this character variety, because it's a representation variety of pi1 of P1 minus the points. And you can compute the dimension, and it tends to be, it gets big pretty quickly. I mean, so the next interesting case are surfaces. So it's always even dimensional. I mean, these are actually hyper-Kähler manifolds. So it's even dimensional. So the next case are surfaces, and those are interesting too. Well, all of them, but sort of you could say, okay, if rigid is 1 point, what's the next case? It will be surfaces, and these have to do with sort of this affine the algebras. So yeah, but in terms of describing specific points on these varieties, I don't know if you can say something very general.
So, and the connection to modularity type questions, you know, the modularity.
Well, you see, my original entry point on this subject was many years ago that Brian Connery was proposing people to find ways to construct modular forms, or L series rather, that one can compute with, that were beyond sort of the kind of things that were known or common. And I thought, okay, well, maybe this modus would be a good way. And this kind of is what pushed this whole project for me. And so it's a little bit, let's see, my experience has been that finding the automorphic part is much harder than dealing with the L function. So somehow you can produce these L functions without having any automorphic. You know that it must exist, and maybe you even know the shape of it and so on. But finding it could be much harder than dealing with the L function alone. So if your focus is the L function, then you can go further than if your focus is the automorphic side. In numerically, I mean, I don't mean theoretically. So you can, in Magma, you can compute with these hypergeometric things of rank 4, and there are only a few examples where people have managed to actually prove that they come from these paramodular forms.
Yeah.
Yeah.
Thank you.
Yeah. No, thank you.
Beautiful talk.
Thank you. Thank you so much.
Thank you, Professor.
All right. So I'll see you on Thursday.
Yeah, thanks.
Okay. Bye-bye.
Pawan, you can end the meeting and yeah. Bye.
Asking the question.